This is section 10.3, polar curve and polar coordinates. So we are going to see some other curves. Previously we saw parametric curves, and then we computed some tangents and areas and arc lengths. So this time we are going to see polar curves coming from polar coordinates, and then later we will compute again tangents, arc length and areas on these curves. So these are some special curves, some of which are familiar to us and others are completely new. So we know that we have a rectangular coordinate system, also called Cartesian coordinate system. So essentially a point in 2D is given by its coordinates x and y. Now what we introduce here is a polar coordinate system. Again, the point in this system will be located with two coordinates, but this time first coordinate is r, which is the distance between the point and the origin. Origin is also called a pole. And the second coordinate will be angle, that this ray from the origin to the point makes with the x-axis, so the usual angle here. So rectangular coordinates or Cartesian coordinates x and y are the distances from x-axis and y-axis, while in polar coordinates the first coordinate will be the distance between the point and the origin, and the second coordinate is the angle that the ray makes with the x-axis. So that's the difference, and obviously there is a link between x, y and r theta, and we will see that. So just to clarify again, we have a point in the plane, and in case of the polar coordinates, the information that we need is the distance from the point to the origin, so that's your r, and the angle that this ray OP makes with the x-axis, sometimes also called polar axis. So essentially it is the distance from the origin and the angle between the x-axis and the ray here that makes OP. We will see that we will have several ways to represent the same point in polar coordinates. It's a little bit different from the Cartesian coordinates. Angle goes in our usual way counterclockwise. It's a positive angle. What happens when r is 0? Well, we are at the origin or at the pole. So in that case, this is just the center of the system, and angle is free to run as any real number. We will see angle, usually we go from 0 to 2 pi, but actually angle can be any real number, so it could be also negative, positive, etc. Another interesting thing is for a given point, so again we have r, the distance between the point and the origin, and the angle theta that the ray makes with the x-axis. What we can do also, and this is a convention that will be very useful, we can use minus r. Also, what happens with minus r? So we have the point here. If I do the minus r, I have, let's say, a reflection through the origin, and I'm here. So essentially this is another point. Now what I can do is represent this point here with the negative r, and we will see how it works. But this is just interesting to realize that we can actually put minus in front of r. Obviously angle can be positive and negative, right? So we will see how these things work. It's very interesting. Another observation is when r is positive, because now we know it can be positive or negative. It's our choice. When we take r positive, the point lies in the same quadrant as the angle. So if I open the angle here and I stop, the r and the is positive, so the point is at the same in the same quadrant as the angle. If r is negative, the point will be in the opposite quadrant. So if here the point is in the first quadrant, if I have r negative, it will go to the third quadrant. Obviously, point negative r theta is represented also as r theta plus pi, so essentially we are just flipping on the other side. We will see several examples of this. It's very useful. So now, couple of examples. If I want to represent the point in polar coordinates and see where it is in the coordinate system. So I have 4 of these points here. They are in polar coordinates. So the first number is the distance from the origin and the second number is the angle. So the point 2, 0, so the distance from the origin is 2. The angle is 0, angle that the ray makes with the x-axis is 0, so we are actually on the x-axis, and distance is 2. So the point is here in the blue. Now, as we said, we could represent the same point but with negative r, for instance. So if I put minus 2, 0, I will be here. But if I put minus 2 pi, then I will flip here. So essentially, you can play with these. One representation is good enough, but sometimes you'll be asked to represent with in two different ways. So here another example. R is 3. The angle that we make with x-axis is pi over 2. So the angle is pi over 2. So we are up, and then we are 3 units away from the origin. So 1, 2, 3, and the angle is pi over 2. So the point is here. Obviously, point minus 3 comma pi over 2 is reflection in the origin, so through the origin here. So you see what happened. If I just put minus in front of r, I flip on the other side. The angle is the same. So I have my original point, and if I put negative in front, I flip on the other side. If I want to represent this point here, I can also say it's 3 pi over 2, but then I can also add 2 pi. 2 pi over 2, so 2 pi over 2 plus 2 pi, so it would be another representation. I could subtract 2 pi, so then I will have a negative angle here. So there are many ways to represent the same point actually in polar coordinates. If I add 2 pi or subtract 2 pi, I get the same point, it's just rotation, and I end up in the same place. Another example, again, distance from the origin is 2. Angle that we make with x-axis is pi, so we start here, angle pi, and then the distance is 2. So that's what we have now. We could obviously get the same point if I had 2 comma negative pi. So I would get the same point. So essentially we see that one point in polar coordinates can have infinitely many representations actually. I could just keep adding 2 pi or subtracting 2 pi from the angle, and I get a new representation. Here is another example. So here I have the point here 1, so this is the distance from the origin, and the angle is 5 pi over 4. So 5 pi over 4, so the point is here. Now you see the angle brings me into the third quadrant, and r is positive, so I stay in the same quadrant. If the r was negative, I would be here in the first quadrant. So we need to be just careful a little bit. Angle tells me where I am, and then if I have positive r, my point is there, I stay. If the r is negative, I go on the same line but in the opposite quadrant. We will see an example with that. So here another example, 2, 3 pi. Now 2 is the distance from the origin. Now 3 pi. Obviously 2 pi is one circle where I go once around, and then another pi, so 3 pi is here. So this angle is the same as 2 pi, is the same point. 2 pi and 3 pi is the same thing. By the way, I could put 2 minus 3 pi, it would be the same point. Here another example, the distance from the origin is 2, angle is negative 2 pi over 3. So I have my x-axis and the negative angle 2 pi over 3. So obviously this point can be represented in a different way. I can have 2 this angle plus 2 pi. So that way I would be like this. So that would be the same thing. Here minus 3, oops, okay, we have minus in front of the distance r, so that means we flip, we go to the opposite quadrant, and then the angle is 3 pi over 4. So the angle 3 pi over 4 is in the second quadrant. Distance from the origin is 3, but because of the minus, we have a reflection through the origin, so it goes to the opposite quadrant. So here is quadrant 2, because of the minus we are in quadrant 4. Now we can obviously have the same point written differently. So instead of having negative 3, I could have 3 comma, but then I could say negative angle, let's say here. So those are the options. So as soon as you have the minus in front of the r, that means you need to go to the opposite quadrant. So quadrant is given by the angle, you measure it, and then the distance is here 3, and then minus tells me I need to change the quadrant. So those are some of the interesting things. This way we can have infinitely many representations. So obviously if I add or subtract 2 pi, I get another representation. But now we learned also we can change the sign of the r and then add or subtract pi and get the same point. So that's very useful, so we can have several representations for the same point. So here, if I just see a little bit, we know that in Cartesian coordinates every point has only one representation, but in polar coordinates we just realized that one point can have actually infinitely many representations. As soon as we have one of them, we can keep adding 2 pi or subtracting 2 pi from the angle and we'll get the same point. And then we just realize also if we change the r from the positive to the negative and we add pi or subtract pi from the angle, we will get the same point. So it's very interesting. So our original point was distance 1 and angle 5 pi over 4. So the angle r is positive here, so we stay with the angle in the same quadrant. So here we are in the quadrant 3, nothing special. Now we can have different ways of writing the same point. Again, distance is 1, but angle is negative 3 pi over 4. How do we get it? Well, we can take this angle here and subtract 2 pi. We can also add 2 pi. Here we added 2 pi. So we are here, and then we add 2 pi, we spin again. So we get this. If we subtract 2 pi from 5 pi over 4, we get here, this one. So basically, we can subtract 2 pi or add 2 pi, and we are at the same place. And you see the r is the same. Here what happened, we changed r, so here we are in the third quadrant. If I change r, if I have negative, I'll have reflection through the origin. So I'm here in third quadrant and I need to go to the first. Now I need the angle. I need to subtract or add pi to the original angle. So 5 pi over 4 minus pi will give me pi over 4. So this is the angle. 1 would be here, minus 1, we go to the opposite quadrant. So we realize that we have several ways of creating notation for the same point. We can keep the same r, add 2 pi or subtract 2 pi, and we get the same point. Another option is put negative in front of the distance r, and then add or subtract pi from the original angle, simply. So those are two options that we have. These will be useful later on because sometimes we will be asked actually to produce different ways of writing the same point. Some of them with positive r, with negative r, with positive angle or negative angle or whatever. So we are just need to be aware of the situation. We can add 2 pi or subtract 2 pi from the angle and keep the same r, or we can have the minus in front of r and then add or subtract pi from the angle. So that's essentially what is summarized here. You can always add or subtract 2 pi, or add or subtract pi and then put the minus in front of the r, and you are still at the same point. So in polar coordinates, that's what's special. One point has infinitely many representations. Some of them are more useful or cuter than others, but as soon as we have one, we can generate all the others. We will be asked to convert from Cartesian coordinates to polar and from polar to Cartesian. So basically we need a relationship, and relationship is really simple. So you see x is equal to r cos theta and y is r sine theta, right, from the triangle. Angle is here, r is here, the distance from the origin to the point. So x is r cos, y is r sine. What we realize is x is associated with cos. Later on it will be useful for something else. And y is associated with sine. Obviously from the triangle, or even if I add here x squared plus y squared, it will be r squared cos squared plus r squared sine squared. So I can factor r squared, so cos squared plus sine squared is 1, so I'll have r squared equal to x squared plus y squared. So if I need r, I just take the square root. So you see here r, if I take the positive square root or negative square root, depending what I need. And from here, y divided by x is sine divided by cosine, which is tan. So those are the 4 equations that we need if I have polar coordinates, so given r and given theta, and I need Cartesian coordinates or rectangular coordinates. I just plug x is equal r cos theta and y is equal r sine theta. So I plug r, I plug theta, the angle, and I'm done. So straightforward computation. From polar to Cartesian, it's straightforward, there's nothing special there. If I need to convert from Cartesian to polar, so I'm given x and y, while r is given by the radical here of this, and the theta, the angle, will be tan inverse of y over x. So again, Cartesian coordinates are obtained directly from the polar, just plug r and theta, nothing special there. And then if I am given Cartesian coordinates, in order to get r and theta, well, I use these two relationships. So x squared plus y squared is r squared, so I will take the root. And tan of the angle is y over x, so I take tan inverse. Now what will happen is the tan inverse, you can have two different angles that can give you the same answer, right? So basically we need to be careful to see in which quadrant we are. So the angle needs to be chosen in such a way that we are in the correct quadrant. So again, here we know that when I take the square root, I can keep just the positive part or the negative. It's better to keep only positive, so that way we are safer, because then the angle will tell us in which quadrant we are immediately. So that's how we will decide which option to take when we take tan inverse. Okay, so we will check x and y to see which quadrant, in which quadrant is our point originally, and then from that we will choose the angle that corresponds. We will see some examples for that, obviously. So if I have polar coordinates of a point, so distance from the origin is 2, angle is pi over 3, what are the Cartesian coordinates? Well, that's easy, it's straightforward, just plug and play. R is 2, angle is pi over 3, I plug it to get x and y, simple. So here x is 1, y is radical 3, so this is the point x1, y radical 3 in Cartesian coordinates. Obviously we see also that this point is in the first quadrant, right? X is positive, y is positive, so point is in the first quadrant. By the way, we know it from here also. The distance from the origin to the point is 2, and angle is pi over 3. Pi over 3 is in the first quadrant. Now, what happens if I have Cartesian coordinates of the point? So 1, negative 1. And what are the polar coordinates for this point? So first thing, I observe x is positive, y is negative. So I'm in the quadrant number 4. So this will be useful because I need to choose the angle that will bring me to the quadrant number 4. So again, the formula was r squared is equal x squared plus y squared. So x squared plus y squared, so 1 plus 1 is 2. And then I take the root. Again, I have option to take positive root, which is a smart option, or negative root. I always take positive because it simplifies my life, because then I just need to follow the angle. I need to be in the fourth quadrant, so I will make sure that when I compute the tan inverse, I will pick the angle that brings me to the fourth quadrant. Now, how do I find the angle? Well, we know that tan of the angle is y over x. So y minus 1 divided by 1 is negative 1. So tan of the angle is negative 1. So arc tan of negative 1 is the angle. Now we know that tan inverse of 1 is pi over 4. So tan inverse of minus 1 will be minus pi over 4. Now minus pi over 4 obviously is in the quadrant number 4. So which is good news. So I can pick this one or 7 pi over 4. Whichever one you like, it doesn't matter. So one possible way of answering the question, what are the coordinates of the point 1 minus 1? Well, in the polar coordinates, r is radical 2 and angle is negative pi over 4. If you prefer to have positive angle, it's not a problem. You take this, add 2 pi, and you get the 0.7 pi over 4. So angle, you can always add 2 pi or subtract 2 pi as you wish. But you see here, because my r is positive, I'm just making sure that my angle fits with the fourth quadrant. So this simplifies my life. Now from this point on, I can now rewrite this in 10,000 different ways. So here I have r positive, angle negative. Equivalent is r positive, angle positive. I could now say I would like to have r negative. So I could put minus radical 2, and then here I would need to add pi over 2, pi, or subtract pi, depending whichever one you want. So those are the options. Once you have one way of writing the point, you can now spin the angle by 2 pi or minus 2 pi, or you can put the minus here and then add pi or subtract pi from the angle. So from that point on, we can play with it. So here again, find polar coordinates of the rectangular point 1, 1. Rectangular point meaning Cartesian coordinates. So point is 1, 1, so it's first quadrant. So y over x is 1, so tan inverse of 1 is pi over 4. So we know the angle. And then to find the r, the distance from the origin, well, it's x squared plus y squared radical. So x squared plus y squared radical. So r is radical 2 and angle is pi over 4. So this is our starting position, and indeed this point is in quadrant 1, pi over 4 is in quadrant 1, r is positive, so everything is fine. Now from this point on, I can add 2 pi to the angle, subtract 2 pi, I get the same point. I can also decide to have r with the negative sign. So I can have minus radical 2, comma, and then from the angle, I can add pi or subtract pi as I like. So here if I add pi, I'll get minus radical 2 and 5 pi over 4. So that gives me the same point. So once you have one representation, you can get infinitely many others by adding 2 pi or subtracting 2 pi from the point, from the angle. Another option is put the minus in front of r and then add pi or subtract pi. So essentially that's what we have. So this is our point, and then I can spin around like we did here. So I add 2 pi, I can spin around, or I can add pi and then I will be here, and that's why I need the negative sign to bring me up there. So when you put negative sign in front of r, you have a reflection through the origin, so essentially you just go to the opposite quadrant. So if I add pi to this guy, I'll get 5 pi over 4, right, like here, and so the point will be there. And then if I put negative in front of radical 2, it will bring me here. So negative 2, comma, 5 pi over 4. So these are 3 ways of writing the same thing. Obviously, we can generate infinitely many of them. You just keep adding 2 pi or subtracting 2 pi. Or from this writing here with the negative r, you can again add 2 pi or subtract 2 pi from this adjusted angle. So essentially, once you have one representation, you're good to go. Now, an interesting thing also is that we can have some of the equations. So here again, a small quick example, polar coordinates representation from a rectangular point. So 2, 3 is x and y. I need to find r and theta. So x, y, so x squared plus y squared is r squared. So I can take the root, positive or negative. It's wiser to take the positive because then you just need to follow it's easier to pick the angle. So tan of the angle is y over x, so 3 over 2. Now this point is in the first quadrant. So when you take tan inverse of 1.5, you'll get probably the answer will be in the first quadrant. So by choosing r positive, you're fine. So there's nothing special there. If you want to have r negative, well, you plug minus and then you add or subtract pi from the angle. It's not a big deal. So if my angle is here in the first quadrant, if I add pi, I would go to the third quadrant, and then with the minus, it brings me back. So essentially, you can have infinitely many ways of writing your answers. Keep the simplest one. My suggestion is always to choose R positive and then find your angle to be in the correct quadrant, and from that point on you can add or subtract 2 pi infinitely many times. Or if you want to have negative R, well, from here you put minus, and then to this guy you add pi or subtract pi. Oops. So if I have rectangular coordinates here, I need rectangular coordinates for the polar point. So polar point meaning polar coordinates. So R, distance from the origin 3, angle is pi over 6. Okay. X and Y is what I need. Well, from the formulas for X and Y, I just plug R and theta and I get direct answer. So here the answer will always be unique. So there will be no issues there. The only problem is usually when we go from Cartesian coordinates to the polar, because of so many options for R, so R could be positive or negative. That's why we choose always positive to simplify our life. And then arctan, we need to pick the angle that is in the correct quadrant. So here are some polar equations. We know that we can have these equations for our curves. So this is a hyperbola x squared minus y squared equal 9. So that's cute, but what we would like is to have polar equation representing the same curve. So we want to have an expression with r equal some expression of theta. How do we do that? Well, we only have 4 equations, right? X is equal r cos, y is equal r sine. And then we have x squared plus y squared is r squared, then tan theta is y over x. That's all we have. So with that we can play. So here I need x squared minus y squared. So x is this, so I square it. Y is this, so I square it, so I subtract them, and it's equal to 9. So 9 is equal to this, so x squared r squared cos squared minus r squared sine squared, factor r squared. So what do we do with this? Well, we recognize that this is cosine 2 theta. So I have 9 equal r squared cosine 2 theta. I need to find an expression of r equal to something. So I bring cos 2 theta down. So I have 1 over cosine is secant, right? So that's why we have this. So essentially now I take the root. Again, I keep plus and minus just in case, so it's more general. We can pick one or the other. And here obviously secant 2 theta needs to be positive because we have radical. So what are the limitations on the angle? Essentially I need to have cosine positive. So cosine is positive in the first and fourth quadrant. So 2 theta, because of the 2 theta, it's like first quadrant and fourth quadrant is minus pi over 2 to pi over 2, but for theta this is 2 theta, so pi over 4 and negative pi over 4. So those are the limitations on the angle, because under radical we need to have something positive. So that's what happens. We had our hyperbola here in Cartesian coordinates, right? X squared minus y squared equal 9. Equivalent expression in polar coordinates would be this, with limitation on the angle. So this is the same curve, but just written in terms of r and angle theta. So here we have a curve given in polar coordinates, or polar equation, r equal to cosine theta, and we would like to find Cartesian equation. Again, we only have 4 relations. We have r squared equal x squared plus y squared. That's always there. X is always r cos. Y is always r sine. So here we have r equal 2 cos theta. So we know that this equation is always true, this equation is always true. So what do? Well, we have the cosine here, r and x. So we need to convert everything from r and theta into x and y. So the first thing is from here to see what to do with the cosine. So cosine is equal r over 2. So since cosine is r over 2, so x is equal r cosine. So I replace cosine by r over 2. I get x equal r squared over 2, which means 2x is equal r squared. Okay, but r squared is always x squared plus y squared. So I replace r squared by x squared plus y squared. So this is my equation in terms of x and y. So I went from r theta, so from the polar equation, into Cartesian equation. Now obviously I still don't know what is the curve here exactly. So if I complete the square for x, I'll get something like this. And now I recognize that this is a circle of radius 1, center is 1, 0, right? X minus 1, so center is 1, 0, radius is 1. So this means that the circle, you see the center is 1, 0. So it is on x-axis, the center. Just a note. Cosine, x-axis, right? Cosine x. So that's linked. What happens if I have polar equation 2 sine theta? Well, procedure is similar. Sine appears in y equal r sine. So that's cool. So here sine is r over 2, and then I'll plug r over 2 instead of sine here. So I get this equation here. And then r squared is again replaced by x squared plus y squared, obviously. So I get a Cartesian equation. So curve written in polar equation in terms of r and theta, and curve, the same curve written in terms of x and y, Cartesian equation. Now again I will complete the square in y, and I'll realize that this is now a circle. Center is 0, 1, and radius is 1. So my center is on y-axis, right? Y sine, 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 y. You see here 2, radius is 1. It's half of the number here. That's how it works. So in general, these polar equations give rise to curves, and we have a formula for them. So basically, how do we draw those things? Let's start with the simple expressions. R, so r is distance from the origin. R equal 2. And what is not written here is that theta can be any real number. When there is no restrictions on theta, we can take any real number there. So we have r equal 2, and theta can spin, 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 spin. So these are all points that are at distance 2 from the origin. Distance 2, and then we can spin infinitely many times. So this is a circle. So you see circle of radius 2 centered at 0, 0. So it's much easier to write the equation of the circle in polar coordinates or polar equation compared to Cartesian equation, because you will need to write x squared plus y squared equal 4. But here is only r equal 2. Simple, simple. By the way, r equal 1 over 2 is all points that are at the distance 0.5 from the origin. R equal 4 is all points that are at distance 4 from the origin, and theta is free to spin. So theta is going from 0 to 2 pi, or actually it can go from minus infinity to plus infinity, doesn't matter. It produces always the same structure. Now what happens if I have only angle? Angle equal pi over 3. What is not written here is what are the restrictions of r. R can be any real value, positive and negative. So I only have angle once I have angle from my x-axis, and then r can be any positive or negative number. So any distance from the origin, positive or negative, doesn't matter. So this is the angle pi over 3. So what we get actually is a line. So angle is pi over 3. If the angle is pi over 3, tan of pi over 3 is radical 3. So we can have actually Cartesian equation y equal radical pi over 3. Another example of a special curve. So circles and lines are quite easy. Now we have something a little bit different. It's called cardioid because it looks like a heart. And the equation is r equal 1 plus sine theta, and theta goes from 0 to 2 pi. If we keep spinning, it is going to just reproduce the same curve over and over. So how does this work? Well, r is the distance from the origin, theta is the angle with the x-axis. So if I start from 0, sine 0 is 0, plus 1 is 1, so we start here. And then as angle goes from 0 to pi over 2, sine is increasing from 0 to 1, right? So at the end I'll have 1 plus 1, 2, so I'll have this distance here. So essentially the distance is increasing from 1 up to 2, and it's 2 when I get to pi over 2 as angle. Then if I go from pi over 2 to pi, sine, what will happen? Well, sine will go from 1 to 0. So r, the distance, will go from 2 to 1, right? We start here and then slowly we go to 1, distance from the origin. When the angle is opened, you see angle is opened up to pi. Now the next stage, we go from pi to 3 pi over 2, and again what happens with the sine? Well, sine is negative now. Sine pi was 0, and then when I go from pi to 3 pi over 2, sine becomes negative, and at 3 pi over 2 is negative 1. So it will be 1 minus 1, it will be 0. R will be 0, so distance from the origin will be 0. So that's why we end up at the origin. So distance is smaller, 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 and then we hit the origin. And then the last piece, when we go from 3 pi over 2 to 2 pi, what happens? Well, sine is negative, but it goes from minus 1 to 0. So we start at 1 minus 1 r 0, and then at some point sine will be 0, so the distance will be 1. So we go from here and then slowly complete there. So this looks like a heart, so that's why it's called cardioid. I wrote up here, see 1 plus sine. So we said that y is equal r sine, right? Sine and y are related. You see, y-axis, and this thing is straight up. Plus is up. If I put minus here, I'll get this thing, but reflection in the x-axis, it will be mirror image. It will be turned down. We will have an example with that also. So you see, sine tells me that this is on y-axis, standing up. Plus tells me it's up. Minus would be flipped down. Everything will be just mirror image. So that's something interesting, because obviously I could have the same 1 plus cosine, so I will have heart, but it will be on the x-axis. We will see that also later. These are the steps, slowly, how we draw the curve. Essentially we have r, the distance from the origin, 1 plus sine, so theta goes from 0 to 2 pi, so we have the r, the distance goes from 1 to 2 and then slowly goes to 0 and then goes to 1 again. So essentially this is broken quadrant by quadrant slowly. I did it a little bit faster so you can go, if you wish, step by step. You see the angle here, evolution of angle, and then r, so angle from 0 to pi over 2, and r goes from 1 to 2. You see, from 1 to 2 the distance from the origin. So basically these are all the steps. I skipped this. This is a cardioid down. Why down? You see the minus sign. Okay, here is 2 and 2, so you can factor 2. So I have 2 times 1 minus sign. You see it's flipped down. Sine, sine, sine means you're on the y-axis. The negative sign here means the bubble is down. So if we are trying to sketch this, we start from angle 0, so sine 0 is 0, so we are at R2, so we are here, and then as angle opens, sine is increasing until reaching 1, so then R will be 0, so when we are at pi over 2, we are here, and then from pi over 2 to pi, we are on the negative side, and then again essentially is the similar procedure as previously, but what is important, we will memorize obviously these shapes, it's not a big deal. What matters is how do you memorize it. Sine is related to y-axis, and then minus, your bubble is down. If it's plus, bubble is up. If I have cosine, bubble is on x-axis. If I have the minus with the cosine, it is on the other side. So we will see the examples for that also. Again, these are the steps how to draw it based on r. So you see r goes from 2 to 0 and then to 4, the distance. And then step by step, quadrant by quadrant, how it goes. Another shape that we have is a rose, this one with 4 leaves. You see the formula, sine 2 theta. Sine theta is a circle, sine 2 theta is a rose. And again, if we try to produce the sketch, r is this distance from the origin, so when angle is at 0, r is 0, so we are here. As angle opens, when we are at pi over 4 times 2, that means sine pi over 2, the distance is 1. And then from that point on, the distance decreases towards 0, so here. And then as we open, 3 pi over 4, so we are here, but then r is negative, so it goes to the opposite quadrant. So essentially the idea is to know where it starts and the maximum distance with the angle, and then after that is pretty much by the symmetries that you do it. It doesn't really matter all the details, but at least to know how to start a little bit, because these pictures and figures can be quite complex. Again, you see r equals sine 2 theta is a rose with 4 petals, so 4 lobes, and then axis here is pi over 4, and you see we have 90 degrees, all of them. So that's interesting, and we get it from the beginning here. Once you get here, you're pretty much done. After that, you know it's a rose, and then it is tilted a little bit, pi over 4. Again, the procedure to find step by step for each quadrant, it's a little bit long for nothing. If I have cosine, so the other one was sine 2 theta, this is cosine 2 theta, so the procedure is the same, but you see what happens. Cosine at 0 is 1, so I'm here. And when angle is 0, I'm here. And then as I go to pi over 4, double the angle goes to pi over 2, so cosine will go to 0. So you see, as the angle opens here, the curve is getting back to 0. And then it's a little bit complicated to know how it works, but doesn't matter. It just matters for you at least to know where it starts and where it goes a little bit. And you see the difference. Cosine, we are aligned with x-axis. Sine, we had our turn at 45 degrees. So again, it is a rose with 4 leaves, 2 theta, right? So for now we have seen some of the common things. So the circle, r equal to a number. By the way, r equal 2 is a circle radius 2. I could put r equal negative 2, is the same circle. It's just each time I open a little bit, I would go to the other side because of the r negative. Right? We just flip the quadrant. Any angle between 0 and pi over 2, we are here, but if I put r equal negative 2, I'll trace it in the third quadrant. And then the angles from the second quadrant will draw the things in the fourth quadrant. So essentially r equal to any number, positive or negative, is a circle centered at 0, 0. Now we have other circles, and this is what we need to remember also. You see sine, a sine theta. So what happens here, we said sine and y-axis are related. So the circle at 0 is r is 0, and then as I open, sine is increasing from 0 to 1. So as I open, I reach 1 here. So obviously a is a number. If it's 7, then here it will be 7, and then it goes back. So here I can complete the circle as my angle goes from 0 to pi only. And again, it's easy to remember when you have a sine theta, it's a circle. Sine is linked with the y-axis, and the radius is half of the number in front. Okay, and the center is x equals 0, and then y equal a over 2, obviously. And then another circle with a cosine theta. So when theta is 0, cosine is 1, so we are here. And then as we open up to pi over 2, cosine will be 0, so we are here. And then if we go from pi over 2 to pi, we are completing the circle. And again, radius is a over 2. We remember cosine is linked with the x. X is r cos, right? So cosine x-axis, sine y-axis. So these are easy things to remember. Now another special one is r equal some number times the angle. So as I open from 0, r is 0, so bigger the angle, bigger the distance, bigger the angle, bigger the distance. So more I spin, so this is one round, so up to 2 pi, and if I keep going, the spiral will be bigger and bigger and bigger and bigger and bigger, right? So that's interesting. So we have a circle, r equal a fixed number, another circle that is on y-axis, a sine theta, circle on x-axis, a cosine theta, and if I have r equal to angle times some number, I get a spiral. So larger the angle, larger the spiral. And again, summary of these roses with 4 leaves, so cosine 2 theta, and these guys at 0, right, we are here, cosine is 1, so we are here, and then It starts from here. 2 theta, we have 4 leaves. 4 theta, we have 8 leaves, double. Cosine 3 is 3 leaves. Cosine 5 is 5 leaves. So you see, for even, we have double number of leaves. 2 theta, 4 leaves. 4 theta, 8 leaves. But for odd, it's the same number of leaves. Again, some revision a little bit. If I have an angle that is given, R is any real number. So angle means the angle between x-axis and the ray, and then R keeps running. So here pi over 4 is here, so 45 degrees, right? 0 degrees is here, x-axis. If I have pi over 3, so 60 degrees, right? So it's something like this. Pi over 2, so the angle here between x-axis and the ray is pi over 2, and then R goes up and down from minus infinity to plus infinity, so that gives me the line here. So essentially our lines are defined by angle only. Circles, we said circle is a distance from the origin. R equal 1, so it's a circle here, or R equal minus 1 is the same circle. R equal 2 is the green bigger circle, so the distance is 2. Again, center is 0, 0. Here angle is from 0 to 2 pi, but actually angle can be any, going from minus infinity to plus infinity doesn't change anything, it's the same curve. This is a summary of our circles also with the sine and cosine. So you see sine theta, center 0, 1 over 2. Here is 1, so half of the number in front. We said sine and y-axis, they are linked. R equal 2 sine theta. Radius is half of the number here, so radius 1. And again, it is on y-axis. R cosine theta. So now we are on x-axis, because if you try to plot it, cosine 0 is 1, so we are here. And then you come back here at pi over 2, and then when you complete to pi, you're getting back here. So here again, radius is half of the number in front. So here is 1, so half is 0.5, so that's the radius. R equal 2 cosine pi, radius is half of the number, so it's 1. Cosine at 0 is 1, times 2 is 2, so we start here, so you see. So you see the circles with sine, they are on y-axis. Circles with cosine, they are on x-axis. If I put negative sign in front, so minus 1, the circle will flip on the negative side. That's all. So circle here was up on y-axis. If I put negative here, it flips down. Same circle, just down. Minus 2, it flips down, below, on the negative side. Minus cosine, so we had cosine on this side, minus cosine flips on the negative side. And again, sine 2 theta, these curves with 4 leaves, and 3 leaves and 5. So essentially this is just a summary for us to see. And cardioid is another one that we need to remember. So again, sine, which means we are on y-axis, right? So it's a heart on y-axis. And then if I have negative, it will flip down, right? Plus, it's on y-axis facing up. With minus, it's flipped on the other side. 1 plus cosine is again cardioid, but now on x-axis. With plus, it's facing the positive side of the x-axis. With minus, it's facing the negative side of the x-axis. So those are the curves that we need to remember essentially. These cardioids, roses with 3 and 5 and 4 at 8 leaves, just the shape generally, and the circles. Circles are very important because they are easy to remember also, so it's important to just memorize them a little bit. So those are the curves and some of the equations for us in polar coordinates. So you have several examples to solve, and in that different video I will be solving some examples also.